I want to look at just a few more examples of alternating series, and just look at just some more practice questions. So we're going to go ahead and even though it wasn't in order in our book, but we'll do D next. And what I like about D is that it shows another way that an alternating series could be given, and it's where they put the alternating part with an additional part of the sequence itself with that too. And so, if you want to rewrite that and sort of isolate the alternating part, you could put it in the numerators, usually where you see it, and then take that times n, and then you still have 2 to the n minus 1. So that's another way. I mean, you don't have to, but at least we can see that the alternating component is away from the other power. Now, let's take a look at what's happening here. I feel pretty good about its convergence because I have an exponential function in the bottom, so that should have a faster rate than just a simple linear function. And so let's use the alternating series test, right? There's really no choice here. Alternating, let's use it, and hope for the best. I think we'll be okay. So, first thing, let's look as the limit as n goes to infinity of just, the sequence of terms that don't alternate, which is this. And again, you could use L'Hopital's rule. One time through, this would become a 1. This would still be exponential. So we know. I mean, it's pretty. I think it's pretty safe to say that we can easily verify that limit is equal to 0. So that's the first condition. Now, second condition, we need to show that it's decreasing. And it may not be. I mean, maybe it's not as recognizable or readily believable. So here's what we're going to do to kind of really show that this is in fact decreasing. Because if you think about, if you needed to verify that this is decreasing, you need to show that this term, 2 to the n minus 1, any term that you pick, and let's say in the sequence of terms, if it's decreasing, then the next one needs to be smaller than what you just had, which would have been the next one in the numerator would have been n plus 1. The next one in the denominator would have been 2 to the n. And so again, that might not be as obvious. So here's how we're going to just justify that. It's pretty clever, I think. So here's something that is true, that you can very easily believe and prove. For n greater than or equal to 1, for n greater than or equal to 1, 1/2 is always less than or equal to n over n plus 1. And you could try it for n equals 1, you get 1/2 is less than or equal to 1/2. And when n equals 2, you get 2/3. N equals 3, 3/4, 4/5, 5/6, right? 6/7. As you get large, it approaches 1. So we know that this inequality definitely is true. So here's a fancy way to think about 1/2 and introduce this power of 2. Think of it as 2 to the n minus 1 over 2 to the n. That's a fancy way to write 1/2. And so that's still going to be less than or equal to n over n plus 1. Everything's positive here, so we can cross multiply. So n plus 1 times 2 to the n minus 1 is less than or equal to n times 2 to the n. And what I want to do is take this 2 to the n minus 1 and put it over here, and then take this 2 to the n and divide it over there. So now I get n plus 1 over 2 to the n is less than or equal to n over 2 to the n minus 1. And that's exactly what I wanted to demonstrate up there. I just switched the direction, but that's fine. So I can confirm, yes, it is decreasing. So so our I guess function of terms n over 2 to the n minus 1 is decreasing. So we've met both conditions. We know that this is going to converge conditionally, at the bare minimum, by the alternating series test. So I could say thus, our series n equals 1 to infinity of n over negative 2 to the n minus 1 converges. And what I'll do is I'll put in parentheses conditionally. So right now it's only based on the condition that it alternates, right? Until we can show otherwise, converges conditionally by the alternating series test. Okay. Now, if we try to look at the absolute value of that, right? If we try to look at just this component of it, oh, there we go. Right now, we don't have enough, we don't have enough tests to verify that that actually does, in fact, converge. So, and intuitively, we should think that it does, right? Because, we know that we have an exponential power in the bottom that's far greater than linear. So, the terms should be getting to zero fast enough that they should eventually converge to a sum. But right now, we don't have the right test. What we're going to need is what's called the nth root test, which is coming. And so right now we'll just leave it there. Now let's look at B, and for B, so if you think about using alternating series test, it's not going to be conclusive, because right away I can tell that the limit as n goes to infinity of just the positive part, right, of n plus 1 over n, that equals 1. Not 0. So that's not a guarantee that this diverges. I would just need some more information. But what I can do, however, is use that to my advantage and prove that this diverges not by the alternating series test, but by the nth term test. Because think about that for a second, like the limit as n goes to infinity of negative 1 to the n plus 1, times n plus 1 over n, that's going to be bouncing back and forth between 1 and negative 1. So that will not exist. And does not exist is not 0, right? So I know that this will diverge, again, not by alternating series test, but by the nth term test. So it diverges by nth term test. Okay. Now, there are some more problems in example 2, and I feel like part A, that I would say you should feel comfortable doing that. And you could check, you could check your response against something that's very close to what we did earlier, really close to A, right? Like 1 over n, 1 over root n. So those are very similar. But let's take a look at let's take a look at part B here for a second and think about like this in this particular problem. What we want to look at is what gets bigger, faster, factorials or exponentials. And so if I look at again, kind of like if we try to use the alternating series test, we're not going to get 0. These terms are getting larger because the n factorial gets larger faster than 2 to the n. So this one actually will diverge, again, not by the alternating series test, but by the nth term test. So we could say the limit as n goes to infinity of negative 1 to the n factorial over 2 to the n doesn't exist. And again, it's sort of like thinking like, yeah, you're alternatingly getting larger in one direction than the other, right? So you're alternating positives, negative, but they continue to get greater and greater and greater. So it doesn't exist, doesn't converge to anything. And so therefore, by the nth term test, I know that series is going to diverge. By nth term test, series diverges. Now, I think I had mentioned too about there's the nth root test, and there's also a ratio test, and both of those are helpful. We'll look at next week, but both of those are also helpful when you are dealing with factorials and powers of n. And so I want to do one more. Let's look at part C, and this one here. So again, I've got it alternating. Great. So let's use alternating series test. Let's make sure that it works. So first, let's look at the limit as n goes to infinity of 6 over n squared plus 1, which is pretty easy to verify that that's 0. That's the first thing we need to verify. Then second, let's see what kind of function, can we claim it's decreasing? And I think, again, it's pretty straightforward that if you make your denominator bigger, the overall fraction will become smaller. So I can say that sequence of terms, yes, is decreasing. There's no clever way to demonstrate that. We know it's decreasing. So we know that this will converge at least conditionally by the alternating series test. So this converges, and at least I'll put in parentheses, conditionally to start with, by the alternating series test. Now, let's think about its absolute value. Let's now consider, what if you took away the alternating part and we just focus just on this? Oops. Thought I picked a different color. There you go. So if we focus on, what if it's just n equals 1 to infinity of 6 over n squared plus 1? Well, this is going to behave a lot like 1 over n squared. So I'm going to use the limit comparison test, right? So let's compare to the series n equals 1 to infinity of 1 over n squared, which converges, right, by the p-series test, which converges by p-series test. Okay, so then I'm going to observe, right, I'm going to note that the limit as n goes to infinity of what I'm interested in, 6 over n squared plus 1, compared to the known series, 1 over n squared. And again, I like on the AP exam, they may be a little bit more lenient than I am. I like to see this one step here, n squared plus 1. Go ahead and flip your fraction, so it's n squared over 1. So it should be pretty clear limit is equal to 6. And that's a finite number, right? That actually converge to a value. So then by the limit comparison test, I know that our series will also converge. So by limit comparison test, and I probably should tell what series I'm talking about, since I have 3 series right now going on. N equals 1 to infinity of 6 over n squared plus 1 also converges. And then the fact that I just proved that converged means overall my given sequence actually converges absolutely. So it's a little bit of a stronger meaning to it. So this converges absolutely. So then I could say, like, therefore converges absolutely. And I know that's not the best sentence, but I think you get the gist. Absolutely. And, that's a pretty common question on the AP exam. You have an alternating series, show that does it diverge or converge? And if it does converge, does it converge absolutely or just conditionally? And then it'll probably ask you something about, an approximation is used, calculate the error, because a very common method of calculating error is in fact using an alternating series test error. And we're going to look at that in class on Monday. Now, the last one I want to look at is just, I guess, this sequence alternates. The sequence of terms alternates, but it's a little bit different compared to maybe something that we've already seen, where you wouldn't necessarily have to use the alternating series test to show that this series does in fact converge, and we can even show it converges absolutely. And so again, kind of like just a neat little thing here. But if you take a look at the positive terms, you might notice a pattern. They're all cubes, right? So the positive terms are all cubes. Equals 1 to infinity of 1 over n cubed, which clearly converges by p-series. It's a finite number, right? And then look at what you're taking away. 1/2, 1/4, 1/8, 1/16. Oh, that's a geometric series, right? Which also converges. So n equals 1 to infinity of 1/2 to the n. So my point here is that just because the terms alternate, I guess this is like that 1% example of you could prove that this converges, and actually converges absolutely, and you didn't have to necessarily use an alternating series test. This was just two convergent series that were like intertwined together. Okay, so and like I said, I would say you could try A, but A is not that much different than than really actually, or even part D or part A of the first example. So then like I said, I just wanted to get us a good start on alternating series, and you could certainly start looking at some of the next homework assignment, but we will definitely talk about error on Monday in class.